Today we explore one of the most revolutionary discoveries in physics, Ernest Rutherford's discovery of the atomic nucleus. Rutherford's gold foil experiment revealed that atoms have a tiny, dense, positively charged nucleus at their center, surrounded by electrons. Before Rutherford, scientists believed in the plum pudding model proposed by J.J. Thomson. Thomson proposed that the atom was like a plum pudding, a uniform sphere of positive charge with negatively charged electrons embedded throughout, like raisins in pudding. In this model, the positive charge was spread uniformly throughout the atom, with electrons scattered like plums in a pudding. This model predicted that fast-moving alpha particles should pass through atoms with only small deflections, since they would encounter diffuse positive charge. The maximum expected deflection angle was less than 1 degree, based on calculations assuming uniform charge distribution. In 1909, Rutherford designed an experiment to test this prediction using alpha particles and gold foil. Alpha particles are helium nuclei with positive charge, mass of about 4 atomic mass units, and speeds around 1/20th the speed of light. The setup was elegantly simple. A radioactive source emitted alpha particles toward a thin gold foil, with a zinc sulfide screen detecting scattered particles through flashes of light. The gold foil was incredibly thin, only about 400 atoms thick, ensuring alpha particles would interact with relatively few atoms. What Rutherford's team observed was completely unexpected and revolutionary. The vast majority of alpha particles passed straight through the gold foil, experiencing deflections of less than 1 degree, exactly as the plum pudding model predicted. Here we see the majority of alpha particles traveling through with minimal deviation, suggesting most of the atom is empty space. However, roughly 1 in 8,000 alpha particles was deflected by more than 90 degrees, and some bounced nearly straight back toward the source. These rare but dramatic deflections were the key anomalies that revolutionized atomic physics. Rutherford later remarked that it was almost as incredible as if you fired a 15-inch shell at tissue paper and it came back and hit you. Let's examine the physics and mathematics behind these deflections. The central question became, what atomic structure could possibly cause such enormous deflections of fast-moving, massive alpha particles? The force between charged particles follows Coulomb's law. F equals k times the product of charges divided by distance squared. To deflect a massive, fast-moving alpha particle through large angles requires enormous electrostatic force, which means extremely close approach to concentrated positive charge. Large deflection angle implies small distance of approach, which implies large force. From the scattering data, Rutherford could estimate the size of whatever was causing these deflections. The calculations showed the nucleus must be incredibly small, about 10 to the negative 14 meters, or about 1/10,000th the size of the atom it's. Based on this evidence, Rutherford proposed a radically new atomic model. Rutherford concluded that atoms must contain a tiny, dense nucleus, carrying all the positive charge and most of the mass. In the nuclear model, electrons orbit a tiny central nucleus, with the atom being mostly empty space. This explains why most alpha particles pass through. They travel through the empty space between nucleus and electrons. Only when an alpha particle passes extremely close to a nucleus does it experience the enormous force needed for large-angle scattering. Rutherford derived a mathematical formula predicting the scattering pattern. The number of particles scattered at angle theta equals n0L squared divided by 16r squared times sine to the 4th power of theta over 2. This Rutherford scattering formula matched experimental observations across all scattering angles, providing strong confirmation of the nuclear model. For example, the formula predicts 16 times more particles scattered at 60 degrees than at 120 degrees, matching observations precisely. Let's understand the remarkable scale and density of the nucleus. If we ask how the nucleus compares in size to the atom, the answer is staggering. If the atom were the size shown here, the nucleus would be this tiny dot in the center, about 10,000 times smaller in radius. The ratio of atomic radius to nuclear radius is approximately 10 to the 4th power, or 10,000 to 1. To put this in perspective, if the nucleus were the size of a marble, the entire atom would extend to the size of a football field. The density of nuclear matter is approximately 10 to the 17th kilograms per cubic meter, millions of times denser than ordinary matter. Let's interpret what these results tell us about atomic structure. Most alpha particles pass through empty space far from any nucleus. Only those making close approaches to a nucleus experience large deflections. The probability of an alpha particle passing close enough to a nucleus for large deflection is proportional to the nuclear cross-sectional area. This probability is proportional to pi times the nuclear radius squared, explaining why large deflections are so rare. Rutherford's discovery fundamentally changed our understanding of matter. The experiment definitively established that atoms have a nuclear structure, not a uniform distribution of charge. This discovery paved the way for Niels Bohr's quantum model of the atom and the development of quantum mechanics. Understanding nuclear structure led to the entire field of nuclear physics, including nuclear fission, fusion, and energy applications. The gold foil experiment perfectly illustrates how rare but decisive anomalies can overturn established scientific theories. Let's summarize the key points of Rutherford's revolutionary discovery. Thomson's Plum pudding model, with uniform positive charge distribution, predicted that alpha particles would experience only small deflections. The gold foil experiments revealed that while most particles pass through with minimal deflection, a small fraction was scattered at very large angles. These rare, large deflections could only be explained by a tiny, dense, positively charged nucleus, containing most of the atomic mass. Quantitative analysis showed the nucleus is approximately 10,000 times smaller in radius than the atom, with enormous density. Rutherford's nuclear model revolutionized physics, showing that atoms are mostly empty space, with a tiny, dense nucleus at the center, surrounded by orbiting electrons.